Hello and welcome back to the YOLO Family series. In this video, we will be talking about the YOLOv4 network and we'll summarize some of the main points from the paper. And the paper's title is YOLOv4 Optimal Speed and Accuracy for Object Detection. So some of the concepts that we'll be discussing in this video involves the Bag of Freebies, and then we'll talk about the Bag of Specials. Then we'll start mentioning some of the architecture modifications that have been implemented on the YOLOv4 backbone. And finally, we'll take a look at the experiments and results. So first, let's introduce the YOLOv4 network. Last time, we talked about YOLOv3, and YOLOv3 is not the last product of the YOLO family. And several versions were later published, such as the scaled YOLOv4, YOLOv5, PP YOLO, all by different authors in 2020 at a very short distance from each other. So after Joseph Redman stopped working on YOLOv3, there were other authors who joined and contributed to the development of the later stages of the YOLO architecture. And some of the major modifications that have been made on YOLOv4 was to make it a real-time detection, object detection network, and they give a priority on conducting the training procedure only on a single GPU. So they wanted to make the YOLOv4 network more efficient, and they only want to implement the training procedure by using a single GPU. So the author's intention is for vision engineers and developers to easily use their YOLOv4 framework in custom domains. So they wanted to improve the YOLOv3 network. That was the final work of Joseph Redman, and they wanted to make it more efficient so that it could be trained and deployed in custom domains. So when you read the YOLOv4 paper, one thing you will notice is that these two terms will be mentioned a lot when you read the paper. So one of them is Bag of Freebies and the other one is Bag of Specials. So when they decided to modify the YOLOv3 network so that it could be more efficient, they introduced a lot of techniques. And since all of the modifications are introduced on the backbone and on the detector, and since their number is a lot, they grouped them into two broad categories. So object detection network consists of the backbone and detector. We already know that when we talked about the structure of YOLO. And both the backbone and detector can use the Bag of Freebies and the Bag of Specials. So the set of techniques that they introduced in order to improve the performance of the model and to make it more efficient, these techniques were introduced on both the backbone and the detector. So what is the difference between the Bag of Freebies and the Bag of Specials? Bag of Freebies are a set of techniques that do not affect the overall architecture, but improve the performance. So if the modifications do not involve changing any part of the architecture, then these techniques are categorized under the Bag of Freebies, and the Bag of Specials are the techniques that will affect the overall architecture. So if any of the modifications involve an update on the architecture, then we group them as Bag of Specials. So let's delve into the Bag of Freebies and Bag of Specials a little bit more so that we can understand what the modifications are. So if a set of methods that only change the training strategy or only increase the training cost, they're referred to as Bag of Freebies. So Bag of Freebies essentially are conducted during the training procedure, and when we implement these techniques, there will be a cost associated with the training procedure. That means it might cost us some memory or some computation, but it's worth it because we're going to get some improvement on the performance. So Bag of Freebies are the techniques without affecting the architecture. But these techniques do not involve any modifications on the overall architecture. So as we dissect the name, the bag part of the name refers to a set of methods or strategies, and the freebies part of the name, it just shows the inference accuracy goes up without any cost to your hardware. So essentially, you're getting the additional performance for free. So there are a lot of techniques that they introduced that could fall under the Bag of Freebies. And this is a diagram or a chart or a mind map that you could use to group all of the techniques that were mentioned on YOLOv4 that could be categorized under the Bag of Freebies umbrella. And the Bag of Specials increases the inference cost by a small amount, but significantly improve the accuracy of object detection. So Bag of Specials are implemented during the inference stage and not during the training procedure. And they also improve the accuracy of object detection. And when we implement these techniques after the training procedure during inference, there will be a cost associated for the inference. So when we dissect the name, the specials part of the name just refers to getting something of value at a discount or for cheap. So the Bag of Specials are techniques that will affect the overall architecture. So they involve some kind of modification on the architecture so that we get an improvement on the inference. So there are also a lot of techniques that could fall under the umbrella of the Bag of Specials, and some of them are involved in enlarging the receptive field, and these are additional blocks like SPP, and there are some attention modules such as channel-wise attention and spatial-wise attention that were introduced. These are also modifications on the architecture. And on the neck part of the network, the FPN, PAN, and other networks or feature aggregation networks were introduced and tried. And during the post-processing stage, they tried between a lot of activation functions and non-maximum suppression. So in order to summarize what we have talked about up until now, we can introduce the Bag of Freebies and the Bag of Specials on the backbone or the detector part of the network. So since there are a lot of techniques that were introduced on the YOLOv4 paper in order to make the model more efficient and be trained on a single GPU, they wanted to group them into two categories, and these techniques can be implemented on either the backbone or the detector part of the network. So as you can see on the image, these are all of the techniques that were tried on the YOLOv4 paper, and the ones that are highlighted in green will be the ones that we will be focusing on in this video. Now let's talk about the architecture of the YOLOv4 network. As we have already seen in the video about the structure of YOLO, YOLO is made up of three main components. That is the backbone, the neck, and the head. And some of the modifications that were made on the different stages of the YOLO network can be shown on the image. And on the backbones, they've tried a lot of different networks that could be implemented in order to enhance the performance. On the neck part of the network, they've tried some additional blocks like SPP and special attention modules. And for the path aggregation, they tried the FPN, PAN, and other path aggregation networks. And on the head part of the network, they didn't modify anything. They just used one that was implemented for YOLOv3. So first, let's start on the backbone. As you can see on the image, some of the deep learning neural networks can be trained using a GPU, and some of them can actually be trained using a CPU. If the number of parameters are small and they don't require a lot of computation, we can just train the network using a CPU. But the authors of the YOLOv4 paper wanted to train the YOLOv4 network using a single GPU. So they tried a bunch of networks and tried to select the best one as the backbone. So the authors considered the following backbones for the YOLOv4 object detector. The first one is CSP Resonex 50. The second one is CSP Darknet 53. And the third one is EfficientNet P3. As we have seen on the video about the structure of YOLO, we have already scratched the surface of the cross-stage partial network, or CSPNet. And the CSP Resonex 50 and the CSP Darknet 53 are both based on DenseNet. And DenseNet was designed to connect layers in convolutional neural networks with the following motivations. So the authors of the DenseNet paper, what they did was modify the method introduced on the ResNet paper. And as you remember, in ResNet, they moved the input directly onto the next layer and performed element-wise addition with the one that has already passed through a convolutional operation. But DenseNet has a strong gradient flow, and the error signal can be backprop easily to the early layers. So the modification that was made on DenseNet was, if you have an input feature map, as we can see on the image, you perform some convolution on that input feature map, and you send a copy of that input feature map onto the next stage. And instead of adding them together and merging them, we just concatenate them together, and we perform another convolution, and then send a copy of the previous input onto the next stage, and we concatenate them together. And we do this repeatedly on the dense block, and finally we reach the transition layer. So the DenseNet allows us to separate the different features from the previous part of the network. So as you can see on the image, we have different colors representing the different feature maps that were used at the different stages of the network. and it has less parameters compared to the ResNet network because there is a growth factor of k, and that's constant, and we will have less number of parameters. We'll have diversified features. We can segregate between different feature maps, and DenseNet works well when training data is insufficient. So when we don't have a lot of training data, DenseNet will be the best architecture or network for our task. So CSPNet is just a modification on the DenseNet, and in CSP ResNext 50 and CSP Darknet 53, the DenseNet has been edited to separate the feature map of the base layer by copying it and sending one copy through the dense block and sending another straight on to the next stage. So previously on the DenseNet, we just used the entire feature map and performed some convolution, and then we concatenate the output from the convolution with the previous input feature map. But on CSPNet, we divide the input feature map into two parts, and we send one of the copies, or the partial copy, to be sent on to the next stage, and we preserve or keep the other half and send it directly to the end of the partial dense block. We do not perform any kind of convolution or concatenation on it. But the other copy, or the other partial copy, we do the same thing that we have done on the DenseNet. So we perform some convolution and concatenate, and we do it a bunch of times, and then finally it will be merged with the partial block that we have just sent directly onto the transition layer. So the idea with the CSP ResNext 50 and the CSP Darknet 53 is to remove the computational bottlenecks in the DenseNet and improve learning by passing on an unedited version of the feature map. So when just passing the partial component of the feature map directly to the transition layer, what they found was it improved the learning better than the DenseNet, and it removed some of the computational bottlenecks. So when we introduce the concept of CSPNet onto the normal ResNext 50 and Darknet 53, we just call them the CSP ResNext 50 and CSP Darknet 53. And as you remember, we used the Darknet 53 as a backbone for the YOLOv4 network. The next network that they tried was EfficientNet, and EfficientNet was designed by Google Brain to primarily study the scaling problem of convolutional neural networks. And there are a lot of decisions you can make when scaling up your ConvNet. So the EfficientNet, as you can see from its name, they wanted to make the network more efficient. And if you want to increase the performance of your network, there are a bunch of things that you can do. So the three main things that they did on this experiment was changing the input resolution size, because when you increase the resolution of the input image, you can better detect smaller objects, so that will increase your performance. Overall, if you use a higher resolution image than a lower resolution image to train your network, you'll have higher performance when you use a higher resolution. The second was that they can increase the width. Increasing the width might be increasing the number of channels. And the depth means you can make your network deeper. So if you modify your network by increasing the input resolution, or increasing the number of channels, or by making the depth of your network more deep, you can increase the performance. But the problem mentioned by the authors of this paper is if you change any of these parameters, you're going to get a higher cost in terms of computation. So you're going to have to compromise on the computation part of your model, because when you increase the input size or resolution, you need to have a higher end GPU or more GPUs in order to perform computations on the pixels of the higher resolution. So the EfficientNet paper posits that there is an optimal point for all of these, and through search they find it. So what they did was, instead of scaling the resolution, the width, and the depth randomly, they tried to select parameters that are going to scale the network efficiently without costing them a lot in terms of computation. So EfficientNet outperforms the other networks of comparable size on image classification. So we have seen a lot of deep learning neural networks that were used on image classification, but their problem was they couldn't be implemented on a CPU or on an edge GPU. So EfficientNet solves both problems by introducing a network of comparable size to those deep learning neural networks that gives higher performance on, or higher accuracy on, image classification. And the YOLOv4 authors posit, however, that the other networks may work better in object detection setting, and decided to experiment with all of them. So the YOLOv4 authors, they had to select a network that could work for object detection. But EfficientNet has the highest accuracy in terms of image classification. So after they have experimented between the three types of networks, the authors of YOLOv4 just wanted to focus on the CSPNet because they thought it could be better for the object detection task. So in order to select the best backbone network, they tried a bunch of networks that we have mentioned previously, and after performing the experiment, they found that the CSP ResNext50 is considerably better compared to the CSP Darknet 53 in terms of classification on the ImageNet dataset. So we have already rolled out the EfficientNet because we wanted a network that could be better on object detection task. And we're left with the CSP ResNext50 and CSP Darknet 53. And in order to select the best network for our backbone, when they trained the network for classification, they got a higher accuracy for the CSP ResNext50 instead of the CSP Darknet 53. However, when they trained for object detection, conversely, the CSP Darknet 53 was found to be better than the CSP ResNext50 on the MS COCO dataset. So now they're thinking, so we found that CSP ResNext 50 was better than CSP Darknet 53 in terms of classification, and the reverse was true when we tried for object detection. So which network are they going to select? Note that the CSPNet can be applied to different backbones, such as the ResNext and the DenseNet. So the story for the backbone selection didn't end, and we will see which network that they selected for the backbone. They actually picked the CSP Darknet 53 for their backbone because they thought that object detection performance was a better criteria for selecting the network for the backbone than performing better on the classification. Next was a subset of a bag of specials that they introduced on the neck part of the network. So they tried some additional blocks like the SPP, ASPP, RFB, and SAM, a spatial attention module. And on the path aggregation blocks, they tried FPN and PAN. So we can basically classify the neck part of the network into two broad categories. The first one is additional blocks, and the second one is path aggregation blocks. And since we are modifying the architecture of the original YOLOv4, these new blocks that we are introducing can be categorized as bag of specials since we are modifying the architecture. So let's talk about the additional blocks first. So in contrast to the image classification classifier, the detector requires the following. So we need a higher input network size for detecting small-sized objects. We have already mentioned previously, if we want to detect very small objects, we need to train our network using a higher input network size. Second, we need more layers for a higher receptive field to cover the increased size of the input network. And third, we need more parameters for greater capacity of a model to detect multiple objects of different sizes in a single image. So the first additional block that they introduced was the spatial pyramid pooling, or the SPP in short. And we have mentioned that we have already selected the CSP Darknet 53 as a backbone. And once we have extracted the feature map from the tail end of the CSP Darknet 53, we can perform an additional block on the neck part of the network, which is called spatial pyramid pooling. And when SPP was originally implemented, they wanted to detect objects from an image. And in order to detect those objects, what you would do was using a sliding window approach. And after you find the object, we crop the image, and then we send it to a convolutional neural network after resizing the image. And then finally, when we reach some stage inside the convolutional neural network, we perform SPP. So when we tried the sliding window approach, it was computationally very intensive. So they wanted to try a different method in order to increase the performance of the model. And one other problem was when you use a fully connected layer in a deep neural network, you cannot change the input size because the fully connected layer enforces the resolution or the input size that you're going to use for your network. So for object detection tasks, we don't want to use fully connected layers. So on the FastRCNN paper, instead of using fully connected layers, they just used convolutional neural networks. So once you use an input image and then perform some convolution operation, you extract a feature map. And then on the final feature map, you just divide that feature map into different bins or grids. It might be 16 by 16. It might be 2 by 2 or 4. Or it might be 256 dimensional. So, for example, if you have a feature map extracted from an input image, and it has 256 channels. First, we need to divide that feature map spatial-wise into different bins, that is 4 by 4, 2 by 2, and 1 by 1. And then we use a pooling operation, such as max pooling, in order to select the maximum number from those bins or regions. And then we change them into, we convert them into one-dimensional vector and concatenate them together. And when we do this, we can use a different input size for our network. So this can be done for any kind of classification or object detection task if we want to use different input sizes, since it significantly increases the receptive field and separates out the most significant context features and causes almost no reduction of the network operation speed. So we have already seen how it works on classification. So by performing some kind of spatial pyramid pooling on the final feature map, we can convert it into a fixed length representation. For example, if you have an input feature or a feature map of size 13 by 13, you can divide it into a 2 by 2 bin, and the window size for each bin can be A, which is the input feature map size, and N, which is the number of bins, and we divide them together in order to get the window size. And in order to get the stride, we take the floor of A divided by N, and in order to get the window size, we can take the ceiling function of A divided by N. So for example, in this particular example, when we divide 13 by 2, we get 6.5, and the ceiling of 6.5 is 7, so the window size will be 7, and the stride will be the floor of 6.5, which would be 6. So this is just one particular case by using the 2 by 2 bin, which is the middle one that we see on the image. Then we do this for a 4 by 4 bin and a 1 by 1 bin. Then since the number of channels is 256 dimensional, after pulling the 16 values for the first representation, we have 256 16 by 256 dimension representation. Then we have 4 by 256 dimensional representation. And then finally, we have 1 by 256 representation. And then we concatenate them together. And the image on the left side shows us how to perform spatial pyramid pulling for a object detection task. So if you have already computed the bounding box, then you can just use that computed bounding box and put it on the final feature map after performing a bunch of convolution operations. Then instead of pulling on the entire feature map as we did before, we're going to do the pulling operation only on that pre-computed window. So we're going to do a 4x4, 2x2, and 1x1 pulling operation on that window. And we're going to create a fixed length representation, and finally we're going to pass it into the fully connected layers. So when we do this, we're not going to be warping the image, so there is no need to crop and passing different patches of the image when we use a pre-computed window on a feature map. The second additional block that they introduced was a spatial attention module. So what is attention? Attention modules are used to make a CNN learn and focus more on the important information rather than learning non-useful background information. For example, you can consider an image containing a cat, and if you just train a normal classifier network by using the entire image, the model doesn't pay attention to the object that it's detecting. That means anything on the background can affect the decision of the model. But when you introduce attention mechanisms, they generally make the model focus more on the object of interest, which is the cat, and not on the non-useful background information. So generally, attention mechanisms were first introduced in natural language processing, but now they are being utilized in computer vision. And there are basically two types of attention modules. The first one is channel-wise attention, which means we pay attention to the representation on the channels. And the second one is spatial attention, which means we're going to pay attention to specific parts of the image spatially or across the height and width. So let's talk about channel attention in detail. So the first channel attention has been introduced on a lot of models. YOLOv4 was not the one that utilized them, but we see them on other works. It is also called the squeeze and excitation module. So the channel attention helps to pay attention across the channels, and it helps us to identify which channel are more important than others. So channel attention consists of the squeeze and the excitation part. Squeeze means if you have an input feature map with a height, width, and number of channels. First, we compress the spatial information, or we squeeze the height and width information into a 1x1 feature map. So for example, if you have an input feature map with dimensions h by w by c, first you compress them spatially. You compress the height and width information into a 1x1, and we compress it by using global average pooling. to compute the average of all of the features across the height and width. And we can use the formula which is inside the red box to compute the global average spatially across the height and width. That means we just add the pixel intensities or the feature representations one by one, and then we divide them by the height multiplied by the width. Then after we compress the height and width, we do the same channel-wise for every channel. So when we, after the squeezing operation, we're going to have a 1 by 1 by C representation. Then on the excitation part, after we get the 1 by 1 by C representation from the squeeze operation, we change them into a fully connected layer. And as we can see on the image from the right, we have C number of neurons on the first layer. We add another fully connected layer with C divided by R, number of neurons. So we reduce the number of channels by a constant ratio, which is represented by R, or the compression ratio, and apply a ReLU activation function. Then we turn it back into a C representation again and make it a third layer. Finally, this will be passed to a sigmoid layer, and the excitation block will be trained to figure out the weights W1 and W2. So the squeeze operation basically is reducing the representations from the height and width so that we only have information across the channel. And the excitation part has a bunch of neurons that we can train because since we have a fully connected layers, we're going to have weights that are going to connect neurons from different layers. And this part of the network can be trained, and it helps us to learn which channel is more important than other channels. So the different colors on the final feature map we get after the excitation operation represents which channels are more important. So in other words, we're paying attention to the channels. So there was a paper known as the Convolutional Block Attention Module. So this paper combines Bose channel attention map and the spatial attention map. So same as the squeeze and excitation that we have seen before for the channel attention, here we use average pooling and max pooling is also added for getting more distinctive channel features. So originally, in order to compress the information across the spatial dimension, we used average pooling, but now we use Bose max pooling and average pooling on the input feature map, as we can see on the image on the left side. Then we transform them into a multi-layer perceptron, which is represented by MLP. Finally, when we get the output from the excitation, then we have one representation coming from the max pool operation, and another feature map coming from the average pool operation. Then we sum them together, and finally we pass them onto a sigmoid function to get the channel attention. So here on the MLP part, we can train the network to learn the weights W0 and W1, and we have used a ReLU activation function on the hidden layer of the MLP. And on the spatial attention map, so we're going to compress since we want to pay attention on the height, across the height and width, we're going to compress the channel. So when we talked about channel attention, we compressed the height and width into 1 by 1. But now, if we have an input feature map F and generate two intermediate feature maps by using max pooling and average pooling, we compress the channel information and we only have a representation of height by width by 1. So across the channel, we're going to compute the average and we're going to create a feature map which is going to be HW by 1. And we're going to do the same by using a max pooling operation. We're going to select the maximum element across the channel and then prepare another feature map, which is H by W by 1. Finally, we're going to concatenate the feature map that we got from the average pooling and the max pooling operation. And by combining them both, we're going to perform a 7 by 7 convolution. We're going to use a kernel size of 7 by 7. Finally, we're going to pass this onto a sigmoid function. And finally, we're going to have the spatial attention representation. So in order to sum up the convolutional block attention module, we perform the channel attention module first. So given an intermediate feature map with dimension H by W by C as input, the CBAM, or the convolutional block attention module, sequentially infers a one-dimensional channel attention map MC. So the MC just represents the 1 by 1 by C representation that we get from the first channel attention module. Then we perform a spatial attention module, which is going to be represented by MS, and it has a dimension of H by W by 1. So mathematically, we can express this by using input feature map. First, it's going to be passed under MC, which is channel attention. Then we're going to perform multiplication with the input feature map, F, and here the X denotes element-wise multiplication. And during the multiplication operation, we can see that the dimensions for the input feature map is H by W by C, and the dimensions for the output from the channel attention module is 1 by 1 by C. So we can perform some kind of broadcasting in order to broadcast the 1 by 1 across the height and across the width. Then we perform the multiplication. Then we get F prime, which is going to be the output of the multiplication operation between the input feature F and the output from the channel attention. And we pass this on to the spatial attention module MS, and we multiply with F prime, which is going to be the output directly from the channel attention module. And finally, it will give us F double prime, which is going to be the final feature representation. So all of this calculation can be summarized on the figure below, which is shown for the convolutional block attention module. So the modified spatial attention module in YOLOv4. So the authors in YOLOv4, they do not want to use the original convolutional block attention module. So they have decided that they do not need the channel attention, and they wanted to use the spatial attention module only. And when we talked about the spatial attention module, we performed both max pooling and average pooling along the channels. But they decided that they do not want to use the pooling operation, and they replaced it by using a convolution operation, as we can see on the image from the right side. And they just, after performing the convolution operation, they're going to pass the output of the convolution operation to a sigmoid function and then multiply it with the input feature map. Now we have finished the additional blocks of the neck part of the network. The second part is pause aggregation blocks. Previously, when we talked about YOLOv3, we have already seen that they used the FPN for the neck part of the network. YOLOv4 chooses the PAN-net, or the pause aggregation network, for the feature aggregation process. And PAN-net is used as a method of parameter aggregation from different backbone levels, from different detection levels, instead of the FPN for YOLOv3. So when we talked about the structure of YOLO, we have already introduced the pause aggregation blocks. So the bottom-up paths that we have seen from the original PAN is augmented to make the low-layer information easier to propagate to the top. So when we perform convolutions on an input feature map, it's very easy to lose that lower layer information. So in FPN, the localized spatial information traveled upward using the red arrow, as we can see on the image at the bottom. So since we are losing that information as we go deeper into the network, they just directly passed the low-level information onto the top, while not clearly demonstrated in the diagram, the red path goes through about 100 layers. And that's not a good thing, because if you're passing through hundreds of layers in order to pass the lower layer information, it's going to decrease the performance of the network. So the path aggregation network introduced a shortcut path, which is indicated by the green path, which only takes about 10 layers to go to the top N5 layer. So on the PAN-net, we have a bottom-up path, then we have a top-down path, and then finally we're going to have another bottom-up path. And we're going to have a shortcut connection from the low feature map representation to the top, which is only 10 layers up. And this short circuit concepts make the fine-grained localized information available to the top layers. And when we talked about the feature pyramid networks, we just performed the detections on the outputs from the different layers. But on the path aggregation network, we're going to combine the information received from the different layers in the bottom-up path, and we can combine them either by using an addition operation or a concatenation operation. So on the original path aggregation network, they used element-wise addition. But on the modified path aggregation network for YOLOv4, they used a concatenation operation. So in FPN, objects are detected separately and independently are at different scale levels. And this may produce a duplicated prediction and not utilize information from other feature maps. So if we perform detections on the different layers independently, we're going to give some duplicated predictions because some of those representations or predictions that we're making may be very close to each other, and they may not utilize the information from the other layers. But the path aggregation network fuses the information together from all of the layers by using the element-wise max operation. So finally, on the head of the YOLOv4 paper, they used the same procedure that we have already mentioned on YOLOv3. So in YOLOv3, we have already talked about anchor boxes, the bounding box predictions. So all of those things that we mentioned on YOLOv3 will be applied on the prediction or the detection that we're implementing in the head part of the network for YOLOv4. So the final output is going to have the X and Y coordinates for the predicted bounding box, the width and height for the predicted bounding box, and we will have an objectness score and the classification scores. So now we have seen the entire architecture for YOLOv4. So we started with the backbone. For the backbone, we selected CSP Darknet 53 because we thought it was better for detection. And we can see on the left side for YOLOv3, we used the Darknet 53. On the neck part of the network, we used FPN in YOLOv3, but in YOLOv4, they selected path aggregation networks because they fuse information coming from the different layers. And this helps in order to enhance the performance. And the head for both YOLOv3 and YOLOv4 are the same. So they didn't make any modification on the head part of the network. So that's all about the first part of the YOLOv4 paper.